Welcome to the Sleepy Science Facts. I'm so glad you've joined me tonight. Whether your day has been long and tiring, or you simply love the thought of unwinding with the mysteries of the universe, this journey is tailored just for you. All you need to do is sit back, relax, and let the soothing wonders of the cosmos gently guide your thoughts to a peaceful, restful sleep. Tonight, we're not going to focus on just one star, planet, or galaxy. Instead, we'll travel across the vastness of space, from the mysterious dark matter to the ancient light that still reaches us from the universe's distant past. We'll explore the universe's hidden wonders, facts that aren't just meant to amaze but to provide a sense of calm, offering solace in the infinite and quiet expanse of space. These cosmic facts are not just about fascinating details, but about a peaceful understanding of how vast and tranquil the universe truly is. As we wander through the mysteries, some facts may surprise you. Others might remain with you, quietly lingering in your mind as you drift into sleep. These gentle explorations offer a restful journey, inviting you to let go of the day's distractions and relax your mind as you float through the cosmos. And if these serene journeys bring you comfort, feel free to like and subscribe. It helps others like you discover this quiet, peaceful space. So, let's begin our journey by pondering a question that has intrigued scientists for centuries. How old is the universe? For many years, the consensus among astronomers placed the age of the universe at around 13.8 billion years. This estimate is based on measurements of the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang, and calculations about how fast the universe is expanding. This number has been the cornerstone of cosmological theory for decades, but not all measurements align with this conclusion. Some astronomers have observed ancient stars and galaxies that seem to defy the age calculations, suggesting that the universe might be even older than we thought. Could it be possible that our current understanding of the universe's age misses something essential? Perhaps the universe's true beginning was a much more complex event, one that began far before what we recognize as the start. Some cosmologists even propose that the universe does not have a true beginning or end, but instead undergoes cycles of expansion, collapse, and rebirth, stretching across infinite eons. This concept challenges the traditional view of a linear, one-time beginning to the universe. Instead, it suggests that what we think of as the beginning of the universe could have been just one phase in an endless rhythm of cosmic cycles, like the universe taking a deep breath, collapsing, and then expanding again in a never-ending process. It's a thought-provoking idea, the possibility that the universe itself has no true origin, no definite start or finish, just a never-ending flow, one cosmos leading into the next without any real conclusion. Could the universe have existed for longer than we can comprehend, stretching far beyond our current view of time? As we continue to look deeper into the cosmos, one of the most fascinating aspects of space is the discovery of rogue planets. Planets that do not orbit any star, but drift aimlessly through the vast reaches of space. Unlike the planets in our solar system, which revolve around our sun, rogue planets wander alone, untethered to any stellar body. These lonely worlds may have formed as part of a solar system, but were cast out due to the gravitational forces that play out during the chaotic formation of star systems. Alternatively, Some rogue planets may have never been part of a star system at all, forming independently as failed stars. Without the warmth of a nearby sun, these planets are cold and dark, nearly invisible, save for the faint glow they might emit when they pass in front of distant stars. Their lack of sunlight means they experience a kind of eternal night, with no sunrises or sunsets, just a steady, silent rotation through an endless, starry sky. Astronomers believe that rogue planets may be more common than we think. In fact, they speculate that there could be billions of these planets in our galaxy alone, perhaps even more than the number of stars. Each of these wandering worlds exists in isolation, slowly spinning through the void, cut off from the warmth and light of a sun. They serve as a reminder of the vast, uncaring emptiness of space, where even the planets are not guaranteed to have a place to call home. This leads us to another intriguing idea. Could the universe be part of an endless cycle of birth, death, and rebirth? Most cosmologists agree that the universe began with the Big Bang and will continue to expand for billions of years. However, some theories propose that the universe could be cyclical, expanding and contracting over and over again. In these models, the universe doesn't simply end in a cold, lifeless fade or a cataclysmic collapse. Instead, it resets, collapsing in on itself, only to rebound and begin expanding again in a fresh cycle, as if the universe itself is reborn. These cycles could stretch on for eternity, with each expansion and collapse wiping away the structures of the previous cycle, but subtly preserving traces of what came before. Imagine, if you will, a universe that doesn't end, but rather evolves in a continuous rhythm, a pulse that beats across infinite stretches of time. One of the most awe-inspiring features of the universe is the light that travels through it. The oldest light we can observe comes from a time just 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. Before this, the universe was filled with a hot, dense plasma that scattered light, making it impossible for photons to travel freely. But as the universe expanded and cooled, it reached a turning point where light was able to move unobstructed. This light, known as the cosmic microwave background radiation, still reaches us today, providing us with a direct glimpse into the universe's infancy. This ancient light has been traveling across space for more than 13 billion years. It has been stretched by the expanding universe into long, cool microwaves, faint but ever present. This quiet glow is a constant reminder of the universe's earliest moments, when it was still in its formative stages, too young to have formed galaxies, stars, or planets. Even though it is not visible to the naked eye, we can detect it with sensitive instruments, offering us a unique window into the past. As we move forward in our journey, we'll explore more of the universe's fascinating secrets, such as the strange existence of planets made entirely of diamond, the nature of black holes, and how time itself might not flow at the same rate everywhere in the cosmos. But for now, take a moment to reflect on the ancient light that connects us to the earliest days of the universe. It's a quiet, gentle reminder that everything in existence, every star, every planet, and even the space between them, has a deep, shared history. Let's continue our journey through the universe, diving deeper into the mysteries that surround us. We've just explored the ancient light that still travels across space, telling the story of the universe's infancy. Now we turn our attention to the hidden, quiet phenomena that silently shape the cosmos, often beyond our direct perception. Imagine a universe that is constantly in motion, yet so vast that the changes are imperceptible to us. A star's life, a planet's orbit, or even the very fabric of space-time itself can stretch across eons, unnoticed in the rush of our everyday lives. But despite the silence and stillness, the universe is far from empty. It is filled with strange, unseen forces that shape its evolution. One such force is dark matter. Dark matter, though invisible to our eyes, has a profound influence on the universe. It is a mysterious substance that does not interact with light or electromagnetic radiation, making it undetectable by traditional means. Yet, scientists are certain of its existence because of its gravitational effects. Without dark matter, galaxies would not have enough mass to hold themselves together, and the structures of the cosmos, as we know them, would fall apart. It's estimated that dark matter makes up about 27% of the universe's mass energy content, while ordinary matter, the stuff that makes up stars, planets, and us, accounts for only about 5%. The strange thing about dark matter is that we don't know exactly what it's made of. It could be composed of particles that interact very weakly with normal matter, or it could be something entirely different, something that defies the laws of physics as we understand them. But one thing is certain. Without dark matter, the universe wouldn't be what it is. It's the silent glue that holds galaxies together, a hidden structure that shapes the way matter moves and organizes itself on the largest scales. While dark matter may be invisible, it is far from the only hidden presence in the universe. There are also rogue planets, worlds that drift through space, unanchored to any star. These planets may have once been part of a solar system, but due to gravitational interactions or other chaotic events, they were ejected from their original orbit. As a result, they roam freely through space, cut off from the warmth and light of any sun. Rogue planets are incredibly difficult to detect as they emit no light of their own. They are cold, dark, and almost entirely invisible, except when they pass in front of distant stars, blocking a small portion of their light. Still, scientists believe there could be billions of these rogue planets scattered throughout the Milky Way. It's fascinating to think about the number of these solitary worlds that drift through the galaxy, each one a silent traveler in the dark. Imagine the lonely existence of a rogue planet, forever adrift in the cold void, with no sun to light its sky or warm its surface. These planets don't have the beautiful sunrises or sunsets we're familiar with. Instead, they exist in a perpetual state of night, far from the comforting embrace of a star. For them, time moves differently, with no reference point to mark the passage of days. These planets are truly alone, wandering through the cosmos in complete isolation. And yet, they are not without significance. Some scientists speculate that these rogue planets could hold secrets to the early history of the universe. They could be remnants of ancient star systems, survivors of cosmic upheaval. Or perhaps they are a product of a much more mysterious process, one that is yet to be fully understood. Either way, these planets remind us that the universe is full of quiet, unnoticed things, phenomena that exist without fanfare, yet still play a vital role in the cosmic order. Now let's consider the age-old question. Does the universe have an edge? For centuries, humans have wondered whether space is infinite, or whether it has a boundary that we could eventually reach if we traveled far enough. The answer according to modern physics, is more complex than a simple yes or no. According to Einstein's theory of general relativity, the shape of space is determined by its contents. The mass and energy within space influence how space itself curves, and this curvature determines the paths that objects take as they move through the cosmos. Current evidence suggests that the universe may either be infinite or so vast and curved that it loops back on itself. If the universe is truly infinite, it would stretch on forever, with no edge to reach. If it's curved, it might eventually loop back in on itself, meaning that you could travel in a straight line forever and eventually return to where you started, similar to how you could travel around the Earth without ever encountering an edge. This idea of a curved universe is difficult to comprehend, but it provides a fascinating image. Imagine traveling across the universe, passing through distant galaxies and star systems, and eventually finding yourself back at your starting point, having never encountered a wall or boundary. The universe would be like a vast, unending loop stretching beyond our ability to fully grasp. There's a beauty in the thought that the universe might not have a definitive beginning or end, just a continuous journey that loops through time and space. While the shape and structure of the universe are still subjects of much debate, one thing is certain: the universe is vast beyond our comprehension. It is filled with mysteries that we have yet to fully uncover, each one waiting for the moment when science and discovery can reveal its secrets. One such mystery lies in the oldest light we can observe, the cosmic microwave background radiation. This ancient glow is the oldest direct signal we can detect from the universe, a faint relic from the time when the cosmos was young and still forming. The light has traveled across space for more than 13 billion years, slowly stretched by the expansion of the universe into cool microwaves. Though faint, this glow is a constant reminder of the universe's infancy, and it still fills the cosmos today, a quiet echo of the Big Bang. The discovery of the cosmic microwave background was a groundbreaking moment in cosmology. It provided the first direct evidence that the universe had a beginning, and it gave scientists a way to study the early conditions of the cosmos. The photons that make up this ancient light have been traveling for more than 13 billion years, carrying with them the memory of a time when the universe was still in its formative stages. The fact that we can still detect this ancient light is a testament to the vastness of space and the incredible distances that light can travel over time. It's a reminder that the universe is constantly changing, evolving, and expanding, but that some things, like the cosmic microwave background, remain with us, a faint but ever-present connection to the universe's past. As we continue our journey through the cosmos, we move from the observable to the mysterious, from the light that has traveled across billions of years to the quiet forces that shape space-time itself. The universe is full of hidden phenomena, things that exist quietly in the background, affecting everything in ways we don't often notice. Time itself, for example, isn't as constant as we might think. It bends, slows, and stretches in the presence of gravity, and it's a key to understanding the fabric of the cosmos. One of the most fascinating features of space is the way gravity influences the flow of time. According to Albert Einstein's theory of general relativity, the stronger the gravitational field, the slower time flows. This is called gravitational time dilation and is not just a theoretical concept. It has been confirmed through experiments. The effect is subtle but profound, especially near massive objects like black holes. Imagine if you could hover just outside the event horizon of a black hole. Time would move much slower for you than it would for someone far away from the black hole. A minute spent near a black hole might be equivalent to hours, days, or even years for someone farther away. This stretching of time is caused by the immense gravitational pull of the black hole, which warps the very fabric of space-time. Interestingly, this isn't just an abstract concept. We can observe this phenomenon in action with things like GPS satellites. Because these satellites orbit the Earth, they experience slightly weaker gravity than we do on the ground. As a result, their clocks tick just a tiny bit faster than ours. Engineers must account for this difference in order to keep GPS systems accurate. So, the next time you use a GPS, you're indirectly experiencing the effects of gravitational time dilation, a small but real example of how time behaves differently depending on where you are in the universe. But time dilation doesn't just occur near black holes. In fact, it's a widespread effect that we experience every day, although it's typically too small for us to notice. Every time we climb a mountain or travel at high speeds, we're subtly experiencing time differently than if we were at sea level or standing still. The higher you go, the weaker the gravitational pull, and the faster time runs. In fact, time runs just slightly faster at the top of Mount Everest than it does at sea level, though the difference is minuscule, only a few nanoseconds. So, time itself is flexible. It's not as constant as we often imagine it to be. Just as space bends around massive objects, so does time. But this is just one of the many curious features of the universe that we're beginning to understand. As we continue our journey, let's shift our focus to another concept that challenges our intuition: the nature of the vacuum of space. When we think about space, we often picture it as an empty, quiet void, nothingness. But in reality, even space is not truly empty. According to quantum physics, the vacuum of space is far from devoid of activity. It's filled with tiny fluctuations, random particles and antiparticles that constantly appear and disappear, popping in and out of existence. This process, known as quantum fluctuations, occurs at every scale, from the smallest particles to the vastness of the universe itself. In fact, this constant bubbling of activity is one of the reasons why space itself is not truly empty. Even in the deepest, darkest reaches of the cosmos, far from stars or galaxies, space is filled with these quantum fluctuations. These fluctuations don't just exist in the small-scale world of particles. They can also have large-scale effects. In fact, some scientists believe that quantum fluctuations played a key role in the formation of the universe. During the early moments of the Big Bang, space expanded at an unimaginable rate in a process known as inflation. This rapid expansion stretched out tiny quantum fluctuations, magnifying them to the size of the observable universe. These fluctuations became the seeds for all the matter and structure we see today. Galaxies, stars, and planets all began as small random variations in the density of matter, imperceptible ripples in the fabric of space-time. This process reminds us that the universe is full of motion, even when it seems still. Beneath the calm exterior of space, there's a constant dance of probabilities, a hum of creation and disappearance. It's as if the universe is always on the verge of something new, with the seeds of every galaxy, star, and planet buried deep within the very fabric of space itself. Now, let's shift our gaze back to the far reaches of the cosmos, where galaxies and stars drift through space. Imagine looking out into the vast expanse of the universe and seeing something so far away that it defies our comprehension. We can observe galaxies that are billions of light years away, yet they're not as they are today. The light we see from these distant galaxies began its journey long ago, sometimes millions or even billions of years ago. This means that when we look at a galaxy, we're not just seeing its present state, we're seeing its past. We're looking through a kind of time machine, peering into the distant past of the cosmos. The light that left a galaxy billions of years ago has traveled across space, slowly stretching and shifting along the way. By the time it reaches us, the light is not only faint, but it has been stretched into longer wavelengths, shifting from visible light into infrared. This phenomenon is known as redshift, and it's one of the key tools that astronomers use to measure the distance to far-off galaxies. Redshift occurs because of the expansion of the universe. As the universe grows, it stretches the space between galaxies, and this stretching causes the light traveling through space to lengthen, shifting toward the red end of the spectrum. The farther away a galaxy is, the more its light is redshifted. This is how astronomers measure the expansion of the universe, and it also gives us a glimpse into the history of the cosmos. By studying the redshift of light, scientists can determine how far back in time a galaxy existed when its light was first emitted. In a sense, we're looking at ancient snapshots of the universe, frozen in time. The light that we see from distant galaxies today was emitted when the universe was much younger. And this gives us clues about how the first galaxies, stars, and even the first black holes formed. While this might seem like an abstract concept, it's a powerful reminder of how vast and interconnected the universe is. When we look up at the night sky, we're not just seeing distant stars and galaxies, we're looking back in time, seeing the universe as it was millions or billions of years ago. Every speck of light that travels across the cosmos carries with it the memory of the universe's history, a history that stretches across eons. In the next chapter, we'll explore some of the most mysterious objects in the universe. Black holes. These invisible giants are both frightening and fascinating. Their immense gravitational pull consuming everything in their path, including light itself. But black holes also have an unexpected role in the universe, one that may surprise you. As we venture further into the quiet expanse of the universe, we now focus on some of the most mysterious and elusive objects in existence. Black holes. These enigmatic forces of nature have captured the imagination of scientists and the general public alike. Black holes are often seen as the universe's ultimate cosmic vacuum cleaners, devouring everything in their path, including light itself. But their influence on the cosmos goes beyond their insatiable hunger. They play a crucial role in shaping the structure and evolution of the universe. First, let's explore what a black hole truly is. At its most basic level, a black hole is a region in space where gravity is so strong that nothing, no matter, no light, can escape. This intense gravitational pull is the result of a massive amount of matter being compressed into an incredibly small area. The core of a black hole, known as the singularity, is where this mass is concentrated, and it represents a point where the laws of physics, as we know them, break down. The boundary surrounding a black hole is called the event horizon, and it marks the point beyond which nothing can escape. Once an object crosses the event horizon, it's pulled inexorably toward the singularity, where it is crushed under the immense gravity. This region is often described as the point of no return, and once something passes through it, it can never be recovered, at least not in any way we can currently understand. While black holes are often depicted as cosmic predators devouring everything in their vicinity, they don't actively suck up matter from across the universe. In fact, they only affect objects that venture too close. Outside of this range, black holes are largely undetectable. They don't suck things in like a vacuum cleaner. Instead, their influence is only felt by objects that stray too close to their immense gravitational field. One of the most fascinating aspects of black holes is their ability to bend space-time itself. According to Einstein's theory of general relativity, massive objects like black holes don't just exert a gravitational pull. They actually warp the very fabric of space-time around them. This means that light, time, and even the structure of the universe itself are altered by the presence of a black hole. As light passes near a black hole, it bends around it, creating one of the most spectacular effects in the universe: gravitational lensing. Gravitational lensing occurs when the light from a distant object, like a galaxy, passes near a massive object like a black hole, bending and distorting the light. The result is often a warped, magnified image of the distant object. In some cases, this effect can create multiple images of the same object, appearing at different angles. Gravitational lensing has provided astronomers with a unique way to observe distant objects, including those that would otherwise be too faint or too far away to see. But black holes don't just distort space-time. They also play a significant role in the life cycle of galaxies. It's now understood that nearly every large galaxy in the universe harbors a supermassive black hole at its center. These supermassive black holes can have masses equivalent to millions or even billions of times that of our Sun. While the exact process by which these giant black holes form is still a mystery, scientists believe that they are closely tied to the formation and evolution of galaxies themselves. Some scientists speculate that supermassive black holes might even act as the engines that drive the formation of stars and galaxies. The intense gravitational forces near a black hole could cause gas and dust to clump together, creating new stars and fueling the growth of galaxies. In this way, black holes might play a crucial role in the cyclical process of galaxy formation, destruction, and rebirth. But the story of black holes doesn't end with their gravitational pull. These mysterious objects also radiate energy in ways that are not immediately apparent. One of the most famous phenomena associated with black holes is the accretion disk, a ring of gas and dust that spirals toward the black hole, heating up and emitting radiation as it does. As matter is pulled toward a black hole, it gets compressed and heated to extremely high temperatures, emitting powerful X-rays and other forms of radiation. This process is so intense that it can outshine entire galaxies, making black holes among the most luminous objects in the universe, despite their ability to trap light. In recent years, scientists have made remarkable progress in capturing images of black holes. In 2019, the Event Horizon Telescope captured the first ever image of a black hole located at the center of the galaxy M87. The image showed a glowing ring of hot gas surrounding the black hole's event horizon, with a dark center marking the location of the singularity. This historic image provided the first direct visual evidence of a black hole's existence, confirming many of the predictions made by Einstein's theory of general relativity. While black holes may seem like silent, invisible giants, they are far from passive observers in the universe. They play an active role in shaping the cosmos, influencing the formation of galaxies, stars, and even the fabric of space-time itself. Their mysterious nature only adds to their allure as scientists continue to uncover new insights into these incredible objects. As we leave the world of black holes, let's turn our attention to another fascinating phenomenon: neutron stars. Neutron stars are the remnants of massive stars that have exploded in a supernova. After the explosion, the core of the star collapses under its own gravity, forming a dense object made mostly of neutrons. Despite their small size, typically just 20 kilometers in diameter, neutron stars are incredibly massive, with a density so high that a single teaspoon of neutron star material would weigh billions of tons. Neutron stars are known for their extreme gravitational and magnetic fields. Some neutron stars, called magnetars, have magnetic fields that are trillions of times stronger than Earth's magnetic field. These powerful magnetic fields can cause intense bursts of radiation, including gamma rays and X-rays. Despite their small size, neutron stars are incredibly powerful, emitting energy and radiation in ways that we're only beginning to understand. Another fascinating aspect of neutron stars is their pulsar behavior. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As the pulsar spins, these beams sweep across the sky, creating a rhythmic pulse of radiation that can be detected by telescopes. Pulsars are often used as cosmic clocks, as their regular pulses are incredibly precise. In fact, pulsars are so reliable that they have been used to measure distances in space and even to test the predictions of general relativity. Neutron stars, like black holes, challenge our understanding of the universe. They are extreme objects, pushing the boundaries of physics and providing us with a glimpse into the most extreme conditions in the cosmos. They remind us that the universe is full of surprises, objects that exist in ways we can barely comprehend, but that play a crucial role in the fabric of the cosmos. As we continue our journey through the vastness of space, let's turn our focus toward the largest and most mysterious structures in the cosmos, the cosmic web. The universe is not a random scattering of stars and galaxies, but rather a vast interconnected structure that stretches across billions of light years. This structure, made up of filaments of dark matter and gas, forms the backbone of the universe, guiding the movement of galaxies and shaping the very nature of space itself. The cosmic web is a massive network of threads that connects galaxies and galaxy clusters. These filaments, made primarily of dark matter, stretch across the universe, linking galaxies together in a delicate cosmic dance. The galaxies within these filaments move along them like beads on a string, drawn by the invisible forces of gravity. In between these threads of dark matter, vast voids exist, regions of space where very little matter is found. These cosmic voids can stretch across hundreds of millions of light years, creating empty spaces in the universe that are almost devoid of galaxies or stars. When we look at the universe, it may appear to be a random collection of galaxies scattered in all directions. But when astronomers map the positions of galaxies on the larger scales, a surprising pattern emerges. Rather than being scattered randomly, galaxies form into vast filaments of matter, creating a network that resembles a cosmic web. At the intersections of these filaments, we find large superclusters of galaxies, massive collections of galaxies that are gravitationally bound together. One of the most remarkable features of the cosmic web is the way it mirrors the structure of a neural network. When scientists map the large-scale structure of the universe, the pattern that emerges looks strikingly similar to the neural connections in the human brain. The nodes of galaxies in the cosmic web resemble neurons, while the filaments of dark matter are like the axons that connect them. It's as if the universe itself has been shaped by the same kind of structure that governs our own minds. Of course, the comparison to a neural network is purely structural. The universe doesn't think or reason like the human brain, but the resemblance is intriguing. It serves as a reminder that the universe is full of patterns, many of which we are only beginning to understand. The cosmic web is one of the largest and most beautiful patterns in the universe, a structure that connects galaxies, clusters, and voids across vast distances. Yet despite its vastness, the cosmic web is largely invisible to the naked eye. We can't see the dark matter filaments that form the web, but we can observe their effects. By studying how galaxies move and how light is bent as it travels through space, astronomers can infer the presence of these filaments of dark matter. The cosmic web is like the hidden skeleton of the universe, an invisible framework that shapes the distribution of galaxies and guides their motion. But the cosmic web isn't the only invisible force at work in the universe. There are also mysterious regions of space where gravity behaves in strange and unexpected ways. One of these areas is the Great Attractor, a gravitational anomaly that exerts an enormous pull on galaxies within our local group. The Great Attractor is located in the direction of the constellation Centaurus, and it seems to be drawing galaxies toward it, including our own Milky Way. But what exactly is the Great Attractor? Scientists don't know for sure. It's a region of space that is incredibly dense, but it's hidden behind a part of the Milky Way, making it difficult to observe directly. We can't see what's causing the gravitational pull, but we can measure its effects. The Great Attractor is responsible for the movement of galaxies in our local group, pulling them toward it at incredible speeds. Beyond the Great Attractor lies another mysterious region known as the dipole repeller. This region is an enormous cosmic void, a vast emptiness that appears to be pushing galaxies away from it. It's located behind the Great Attractor, and is one of the most unusual features of the universe. The dipole repeller is so massive that it's exerting a gravitational force on galaxies, pushing them away as if it were the opposite of the Great Attractor. Together, the Great Attractor and the dipole repeller form a kind of cosmic tug-of-war. The Great Attractor pulls galaxies toward it, while the dipole repeller pushes them away. The result is a subtle but significant effect on the motion of galaxies in our local universe. This gravitational dance is just one of the many invisible forces that shape the cosmos. It's a reminder that the universe is not just filled with visible matter and light, but is also governed by unseen forces that influence everything in ways we're only beginning to understand. As we move from these invisible forces to something more tangible, let's turn our attention to another cosmic mystery, the way that galaxies themselves evolve and interact with one another. Galaxies are not isolated islands in space. Many of them are part of larger galactic groups. Some galaxies orbit one another in a dance that can last for billions of years, gradually merging to form larger galaxies. The Milky Way, our home galaxy, is no exception. It has dozens of smaller galaxies orbiting around it, forming a kind of galactic family. One of the most famous of these companion galaxies is the Andromeda Galaxy. Andromeda is the largest galaxy in our local group, and it's on a collision course with the Milky Way. In about 4 billion years, the two galaxies will collide and merge, forming a new, larger galaxy. Interestingly, the outer halos of both galaxies, their vast clouds of gas and dark matter, are already overlapping, meaning they've already begun to touch. This cosmic merger won't be a violent crash. Instead, it will be a slow, graceful blending of two massive galaxies. As they collide, the stars in both galaxies will mostly pass by each other without colliding. The merger will take billions of years to complete, but when it's finished, the two spiral galaxies will have formed a single elliptical galaxy. But even as galaxies collide and merge, there are other, quieter processes at work. The vacuum of space, for instance, is not as empty as we once thought. Even in the darkest reaches of the cosmos, far from any stars or galaxies, space is never truly empty. According to quantum physics, even empty space is filled with tiny fluctuations, particles and antiparticles that spontaneously appear and disappear. This constant bubbling of energy is a phenomenon known as vacuum energy, and it has profound implications for our understanding of the universe. One of the most intriguing consequences of vacuum energy is its connection to dark energy, the mysterious force that is driving the accelerating expansion of the universe. Dark energy is thought to be responsible for the increasing speed at which galaxies are moving apart. It's a force that permeates all of space, yet we have no direct way of observing it. Dark energy is thought to make up about 68% of the universe's total energy content, but its nature remains one of the greatest mysteries in cosmology. As we continue our exploration, let's take a moment to reflect on the vastness and complexity of the universe. From the invisible cosmic web that connects galaxies to the mysterious forces of the Great Attractor and the Dipole Repeller, we've only scratched the surface of the universe's true scale. The universe is far more than just stars and galaxies. It's a dynamic, living system filled with unseen forces and structures that shape the cosmos in ways we are only beginning to understand. As we move deeper into our exploration of the universe, we come to one of the most perplexing and awe-inspiring phenomena that govern the cosmos, the expansion of the universe. For centuries, scientists believed that the universe was static, unchanging, and eternal. However, in the 20th century, astronomical observations revealed that the universe is actually expanding, with galaxies moving away from each other at ever-increasing speeds. This discovery has reshaped our understanding of the cosmos and raised new questions about its ultimate fate. In 1929, astronomer Edwin Hubble made a groundbreaking discovery that would change our understanding of the universe forever. He observed that galaxies were moving away from us in all directions, and the farther a galaxy was, the faster it was receding. This relationship became known as Hubble's law, the idea that the universe is expanding uniformly, with galaxies receding from one another at a rate proportional to their distance from each other. This was the first direct evidence that the universe itself was growing in size. The idea of an expanding universe was initially met with skepticism, but it was soon confirmed through further observations. The most compelling evidence came from the discovery of the cosmic microwave background radiation, the afterglow of the Big Bang. This faint radiation, which permeates the entire universe, provides a snapshot of the universe when it was just 380,000 years old. Its discovery in 1965 by Arno Penzias and Robert Wilson provided the final confirmation that the universe had a beginning and has been expanding ever since. But the story of the universe's expansion doesn't end there. In the late 1990s, scientists made another startling discovery. The expansion of the universe is accelerating. While Hubble's law showed that galaxies were moving apart, the idea that the rate of expansion could actually increase over time seemed impossible. However, observations of distant supernovae, exploding stars, revealed the light from these supernovae was fainter than expected, indicating that they were farther away than previously thought. This suggested that the universe's expansion was not only continuing but accelerating. This unexpected acceleration is driven by a mysterious force known as dark energy. Dark energy is believed to make up about 68% of the total energy content of the universe, yet it remains one of the greatest mysteries in cosmology. Unlike ordinary matter and dark matter, dark energy doesn't exert a gravitational pull. Instead, it works in the opposite direction, causing the expansion of the universe to speed up over time. But what exactly is dark energy? Is it a property of space itself, or is it something more fundamental? While we don't yet understand the true nature of dark energy, its effects are clear. It's causing galaxies to move away from one another at an ever-increasing rate, and it's pushing the universe toward a future where distant galaxies will be unreachable, their light stretched beyond detection. This acceleration of the universe's expansion has profound implications for the future of the cosmos. As galaxies move farther apart, they will become increasingly isolated, and the night sky will gradually fade as the universe continues to expand. One possibility is that the universe will eventually reach a state known as the Big Freeze. In this scenario, the expansion of the universe continues indefinitely, with galaxies moving farther and farther apart. As the universe expands, stars will burn out and galaxies will grow darker. Over billions of years, all matter will become more and more spread out, and the universe will approach a state of near absolute zero, where everything is cold, dark, and lifeless. However, there's another possibility, one that suggests the universe might eventually collapse in on itself. This idea, known as the Big Crunch, posits that the expansion of the universe will eventually slow and reverse, causing galaxies, stars, and all of matter to come crashing together in a cataclysmic collapse. While this theory is less widely accepted today, it remains a fascinating concept. If the universe were to collapse, it would end in a fiery, chaotic event, possibly similar to the Big Bang itself. But for now, the prevailing theory is that the universe will continue to expand indefinitely, driven by the mysterious force of dark energy. The acceleration of this expansion raises a number of intriguing questions. Is dark energy a constant force, or does it change over time? Could it be that dark energy is somehow tied to the very fabric of space itself? These are questions that scientists are still trying to answer, and they will likely shape the future of cosmology for years to come. As we contemplate the accelerating expansion of the universe, let's shift our focus to the very fabric of space-time itself. In the realm of general relativity, space and time are not separate entities. They are part of a unified structure called space-time. This four-dimensional fabric is warped by the presence of mass and energy, and it is what gives rise to the force of gravity. Gravity, as we experience it, is the effect of this warping of space-time. Massive objects like planets and stars bend space-time around them, creating the gravitational pull that we feel. But space-time itself is not static. It's constantly evolving, stretching, and bending in response to the objects within it. And just as the expansion of the universe is accelerating, the very fabric of space-time is also stretching. This stretching of space-time has some fascinating implications for the way we perceive the universe. One of the most mind-bending effects of space-time stretching is the phenomenon known as cosmological redshift. As space itself expands, it stretches the light that travels through it, causing the wavelengths of light to lengthen. This is similar to how a stretched rubber band becomes thinner and longer. The light from distant galaxies is stretched as it travels through space, shifting from visible wavelengths to infrared and beyond. The farther a galaxy is from us, the more its light is stretched and the redder it appears. Cosmological redshift is a key tool for measuring the expansion of the universe and understanding its history. By studying the redshift of light from distant galaxies, astronomers can determine how far away they are and how fast they are moving. This information helps scientists map out the large-scale structure of the universe, from the vast filaments of galaxies to the empty voids between them. Another fascinating aspect of space-time is the cosmic horizon, the furthest distance that light can travel in the universe. Beyond this horizon, galaxies are receding from us faster than the speed of light due to the expansion of space. This means that their light will never reach us, even if we wait forever. The cosmic horizon marks the limit of what we can observe in the universe, and it serves as a reminder of the vastness and mystery of the cosmos. As we continue our journey through space-time, it's important to remember that the universe is still full of surprises. The mysteries of dark energy, the expansion of the universe, and the stretching of space-time are just a few of the many questions that remain unsolved. As we move forward, we'll explore the birth and death of stars, the nature of dark matter, and the quiet forces that govern the universe. But for now, let's take a moment to reflect on the enormity of what we've already uncovered. The universe is vast, mysterious, and full of questions that challenge our understanding of time, space, and everything in between. As we continue to navigate the vast stretches of the universe, we arrive at one of the most awe-inspiring phenomena, the life cycle of stars. Stars are the heartbeat of the cosmos, and their birth, life, and eventual death shape the very structure of the universe. From the fiery birth of a star in a dense cloud of gas and dust to its explosive demise as a supernova, or its quiet fading into a white dwarf, stars play a central role in the ongoing evolution of the universe. Let's begin with the birth of a star. Stars are born in vast cold clouds of gas and dust, known as nebulae, which are scattered throughout the universe. These clouds are composed mostly of hydrogen, the most abundant element in the universe. Over time, the gas and dust in these nebulae begin to collapse under their own gravity. As the material falls inward, it heats up, forming a dense core known as a protostar. The protostar continues to contract, and as it does, its core becomes increasingly hot and dense. Eventually, the temperature reaches a critical point and nuclear fusion begins. Fusion is a process in which hydrogen atoms collide and fuse together to form helium, releasing an immense amount of energy in the form of light and heat. This marks the birth of a full-fledged star. The star enters what is known as the main sequence phase of its life, where it will spend most of its existence. During this phase, a star is in a delicate balance. The inward pull of gravity, which is constantly trying to collapse the star, is counteracted by the outward pressure created by the energy released during fusion. This balance keeps the star stable for billions of years. The size and temperature of a star during the main sequence phase depend on its mass. The more massive a star is, the hotter and brighter it burns. The Sun, for example, is a medium-sized star that has been in the main sequence phase for about 4.6 billion years. It's expected to remain in this phase for another 5 billion years, gradually increasing in brightness as it ages. However, massive stars live much shorter lives. A star several times the mass of the Sun might only spend a few million years in the main sequence before it begins to evolve into its next phase. When a star exhausts its supply of hydrogen fuel in the core, the process of nuclear fusion slows down and gravity takes over, causing the core to collapse. This collapse heats the core to extremely high temperatures, causing it to ignite new fusion reactions with heavier elements. As a result, the outer layers of the star expand and the star becomes a red giant. During this phase, the star swells to many times its original size, and its outer layers become cooler, giving the star a reddish hue. The core continues to burn through heavier elements, such as helium, carbon, and oxygen. The outer layers of the red giant are unstable and are periodically shed in powerful stellar winds, creating beautiful planetary nebulae, colorful shells of gas and dust that surround the dying star. Eventually, the star reaches the end of its life. If the star is of moderate mass, like the Sun, it will shed its outer layers entirely, leaving behind a dense, hot core. This core is called a white dwarf, and it no longer undergoes fusion. Over the course of billions of years, a white dwarf will gradually cool and fade, becoming a cold, dark black dwarf, a remnant of the star's former glory. But what happens to massive stars is much more dramatic. When a massive star reaches the end of its life, it experiences a supernova, a powerful explosion that occurs when the core collapses under its own gravity. The energy released during a supernova is so immense that it can outshine an entire galaxy for a brief period, and it is this explosion that creates many of the heaviest elements in the universe, such as gold, platinum, and uranium. The core of the massive star may collapse into a neutron star, which is incredibly dense. Or, if the star is massive enough, it may collapse into a black hole. The explosion of a supernova is a violent cataclysmic event, but it is also one of the most important processes in the universe. Supernova scatter the elements created during fusion into space, enriching the interstellar medium with the raw materials needed for the formation of new stars, planets, and even life. After a supernova explosion, the remaining core can become a neutron star, a highly dense remnant composed almost entirely of neutrons. Neutron stars are only about 20 kilometers in diameter but contain more mass than our Sun. These stars are incredibly dense, and a single teaspoon of neutron star material would weigh billions of tons. Some neutron stars also have incredibly strong magnetic fields, which can produce intense bursts of radiation known as gamma-ray bursts. In some cases, if the neutron star is massive enough, it may collapse further into a black hole. A black hole is an object with a gravitational pull so strong that not even light can escape. The collapse of a massive star into a black hole is one of the most dramatic and mysterious events in the universe. As we reflect on the lives of stars, we realize that their birth, life, and death are not just isolated events. The cycle of stellar evolution is interconnected with the larger processes that shape the universe. Stars are the creators of the elements that make up planets and living organisms. They are the engines that fuel the growth of galaxies, and they are the providers of energy and light that sustain life. But stars do not exist in isolation. They are part of larger structures known as galaxies, vast collections of stars, gas, dust, and dark matter that are held together by gravity. Galaxies come in all shapes and sizes, from small, irregular galaxies to massive spiral galaxies like the Milky Way. Galaxies can contain billions or even trillions of stars, and they are constantly evolving. Galaxies are not static objects. They move, collide, and merge with one another, shaping the structure of the universe. The Milky Way, for example, is on a collision course with the Andromeda Galaxy, and in about 4 billion years, the two galaxies will merge to form a new, larger galaxy. This cosmic dance of galaxies is a slow process, but it is one that has been happening for billions of years, and it will continue to shape the universe for eons to come. As we continue our journey through the cosmos, we now turn our attention to the invisible forces that shape the universe, the forces that govern the formation, movement, and structure of galaxies, as well as the mysterious, unseen matter that permeates the cosmos, dark matter. While we have explored the birth, life, and death of stars and galaxies, much of the structure of the universe remains hidden from our eyes, shaped by forces that we cannot directly detect. At the heart of every galaxy lies an invisible force that holds it all together. This force is known as dark matter, and it is responsible for the observed gravitational effects that shape galaxies and galaxy clusters. Despite making up about 27% of the universe's mass energy content, dark matter does not emit, absorb, or reflect light. This makes it completely invisible to our most powerful telescopes, which are only capable of detecting visible light, infrared, and other forms of electromagnetic radiation. How, then, do we know that dark matter exists? The evidence for dark matter comes from its gravitational influence on the visible matter in galaxies. When astronomers observe the way galaxies rotate, they notice something strange. The stars at the outer edges of galaxies are moving much faster than expected based on the amount of visible matter in the galaxy. If only the visible stars and gas were present, these outer stars should be moving much slower, and the galaxies would break apart due to insufficient gravitational pull. Yet, galaxies remain intact. This discrepancy suggests that there is something else present in galaxies, an invisible mass that is providing additional gravitational pull. This unseen mass is what we call dark matter. It acts like a cosmic scaffold, providing the necessary gravitational forces to keep galaxies bound together. Dark matter does not emit light, but it is crucial for understanding how galaxies form, evolve, and maintain their structure over time. While we cannot see dark matter directly, we can observe its effects in other ways. One of the most compelling pieces of evidence for dark matter comes from the study of galaxy clusters. When astronomers observe galaxy clusters, they find the galaxies within them are moving much faster than they should be, based on the visible mass of the cluster. If dark matter were not present, these galaxies would fly apart. However, the clusters remain intact, held together by the unseen gravitational influence of dark matter. Dark matter also plays a key role in the structure of the universe itself. On the largest scales, dark matter is responsible for the formation of the cosmic web, the vast, interconnected network of galaxies and galaxy clusters that stretches across the universe. Dark matter forms the invisible scaffolding of this web, with galaxies and galaxy clusters aligning along the dark matter filaments. The web of dark matter acts as a guide, pulling visible matter into clumps and creating the large-scale structure of the universe that we observe today. But what exactly is dark matter made of? This is one of the greatest mysteries in modern cosmology. While we know that dark matter is not made of ordinary matter, such as protons, neutrons, and electrons, we have yet to determine its true composition. Some theories suggest that dark matter is made up of weakly interacting massive particles, WIMPs, which are subatomic particles that interact very weakly with normal matter. These particles would be difficult to detect as they don't interact with light or other forms of electromagnetic radiation. Other theories propose that dark matter could be composed of axions, hypothetical particles that are much lighter than WIMPs. Axions, if they exist, would also interact very weakly with matter, making them extremely difficult to detect. Scientists are actively searching for dark matter in laboratories on Earth, using sensitive detectors to look for the faint signals of WIMPs or axions. However, so far, no direct evidence for dark matter particles has been found. Despite the lack of direct detection, dark matter remains one of the most important areas of research in cosmology. Understanding dark matter is crucial for understanding how galaxies form, evolve, and interact. It also holds the key to understanding the large-scale structure of the universe and the ultimate fate of the cosmos. Until we can directly detect dark matter, its mysteries will continue to tantalize us, but its effects on the universe are undeniable. As we turn our attention back to the visible universe, we come to another fascinating subject: dark energy. While dark matter is responsible for the gravitational effects that hold galaxies and galaxy clusters together, dark energy is the mysterious force that is driving the accelerating expansion of the universe. Dark energy makes up about 68% of the universe's total energy content, and yet we know very little about it. Dark energy was first discovered in the late 1990s when astronomers observed that the expansion of the universe was not slowing down, as previously thought, but was instead accelerating. This discovery came from observations of distant supernovae, which revealed that the light from these exploding stars was fainter than expected, indicating that they were farther away than previously believed. The only way to explain this acceleration was by positing the existence of dark energy, a force that acts in opposition to gravity and drives the expansion of the universe. Since its discovery, dark energy has become one of the most mysterious and important concepts in cosmology. Scientists believe that dark energy is a property of space itself, causing the fabric of space-time to stretch and accelerate. It is thought to be a constant force, exerting a uniform pressure throughout the universe. However, the exact nature of dark energy remains unknown. Some scientists propose that dark energy is a manifestation of the cosmological constant, a term introduced by Einstein in his equations of general relativity to account for the static nature of the universe. Others suggest that dark energy might be related to quantum fluctuations in the vacuum of space. Whatever dark energy is, its effects on the universe are undeniable. It is causing galaxies to move farther apart at an accelerating rate, and it is driving the universe toward a future where distant galaxies will be unreachable. As the expansion continues, space itself will stretch, and the universe will grow ever colder and darker. Some scientists speculate that dark energy could even lead to a big rip, a scenario in which the expansion of the universe accelerates so rapidly that galaxies, stars, and even atoms are torn apart. Dark matter and dark energy represent two of the greatest mysteries in modern science. While we may not yet fully understand them, their existence shapes the very fabric of the universe. They govern the large-scale structure of the cosmos, influence the formation and evolution of galaxies, and play a key role in the expansion of the universe itself. As we have seen, the universe is a dynamic, ever-evolving entity, governed by a series of unseen forces and extraordinary phenomena. From the birth and death of stars to the invisible web of dark matter and the mysterious force of dark energy, the cosmos operates in ways that constantly challenge our understanding. But what of the future? How will the universe evolve in the coming billions of years? And what might its ultimate fate be? These questions are at the forefront of cosmological research, and the answers may surprise you. One of the most widely discussed theories about the future of the universe is the Big Freeze. The Big Freeze is a scenario in which the universe continues to expand indefinitely, driven by the ever-present force of dark energy. As the universe expands, galaxies will move farther apart, and stars will burn out one by one. The galaxies we see today, including our own Milky Way, will eventually be separated by vast distances, making them invisible to one another. The universe will grow colder, darker, and more isolated, with stars and galaxies becoming increasingly distant. In the distant future, stars will exhaust their nuclear fuel and burn out. Small stars, like our Sun, will become white dwarfs, their cores cooling and fading into darkness. Larger stars will end their lives in violent supernovae, but even these spectacular explosions will eventually fade, leaving behind remnants like neutron stars or black holes. The black holes, though powerful and mysterious, will eventually lose their mass, through a process called Hawking radiation, a theoretical process by which black holes slowly emit radiation and gradually evaporate. But even this will take an unimaginably long time. Over trillions of years, the universe will continue to cool, and all forms of energy will eventually dissipate. The Big Freeze is the most likely scenario for the distant future of the universe. If dark energy continues to drive the accelerated expansion of the cosmos, the universe will eventually reach a state of heat death, where all energy is evenly spread out and no thermodynamic processes can occur. It will be a universe of complete entropy, where nothing happens and everything is frozen in place. This fate, while a long way off, provides a sobering reminder of the eventual fate of all things. But the Big Freeze is not the only possible end for the universe. Some scientists have proposed the idea of the Big Crunch, a scenario in which the universe's expansion eventually slows and reverses, causing all matter to collapse back toward a single point. In this scenario, gravity would overcome the force of dark energy, and galaxies, stars, and planets would be drawn together into an increasingly dense and hot singularity. The universe would essentially implode, ending in a fiery collapse. The Big Crunch is the opposite of the Big Freeze, and while it was once considered a likely outcome, it has become less plausible as observations of the universe's accelerating expansion suggest that dark energy is dominating the forces at play. A variant of the Big Crunch is the idea of the Big Bounce, a cyclical model in which the universe contracts, then rebounds in a new Big Bang, starting the cycle over again. In this scenario, the universe would go through an endless series of expansions and contractions, like the beating of a cosmic heart. While the Big Bounce is an intriguing idea, it remains speculative, and many scientists lean toward the Big Freeze as the most likely outcome based on current observations. However, there is a more speculative and far-reaching idea that has been gaining attention in recent years: the Big Rip. The Big Rip suggests that the expansion of the universe could accelerate to the point where the very fabric of space-time is torn apart. In this scenario, dark energy would become so powerful that it would overcome the gravitational forces holding galaxies, stars, and even atoms together. The expansion of space would rip apart galaxies, then stars, planets, and eventually atoms themselves. The Big Rip would be a cataclysmic end to the universe, in which everything is torn apart in an ever-accelerating process of cosmic disintegration. This scenario is still a hypothesis, but it's a chilling thought that the universe could end not in a cold, dark silence, but in a violent rupture of space and time. While the exact fate of the universe remains uncertain, one thing is clear: the universe will continue to evolve in ways that we can barely comprehend. The forces at play, from the accelerating expansion driven by dark energy to the gravitational pull of dark matter, will continue to shape the universe for billions of years. And as scientists continue to study the cosmos, they will uncover more about the nature of these forces and how they will ultimately shape the future of the universe. But even as we ponder the far future of the universe, we must also consider the profound implications that our understanding of the cosmos has for us today. The study of the universe is not just about looking backward to the past or forward to the future. It's about understanding our place in the grand scheme of things. Our solar system, our galaxy, and our universe are part of a vast interconnected web of matter and energy we are a small but significant part of this cosmic story. As we continue to study the universe, we are constantly reminded of the extraordinary scale of time and space. The light from distant galaxies that we observe today left those galaxies billions of years ago. The stars we see in the night sky are often long dead, their light traveling across vast distances to reach us. In a sense, when we look up at the stars, we are looking into the past, observing events that took place long before our time. The universe, in its vastness and complexity, exists on a scale that is almost impossible for us to grasp. The study of the universe also forces us to confront questions about the nature of existence itself. How did the universe come into being? What is the true nature of dark matter and dark energy? How do the fundamental forces of the cosmos work? And how did they come to be? These questions are not just the domain of physicists and cosmologists. They are questions that touch on the very meaning of life, existence, and the future of humanity. As we continue to explore the universe, we may not have all the answers, but the journey itself is a reminder of our place in the cosmos. As we continue our journey through the cosmos, we come to one of the most profound and tantalizing questions in science. Are we alone in the universe? The search for extraterrestrial life has fascinated humanity for centuries, and with the advancement of technology, we are now closer than ever to answering this age-old question. But the quest for life beyond Earth is not just about finding another civilization or discovering intelligent beings. It's about understanding our place in the vastness of the universe and asking fundamental questions about the origins of life itself. The idea that life exists elsewhere in the universe has long been a subject of speculation and science fiction. From the ancient Greeks to modern-day astronomers, humans have wondered whether life could exist beyond Earth. For much of history, this question was purely philosophical, but with the advent of modern science, it has become a subject of rigorous study. The search for extraterrestrial life has taken many forms over the years. One of the most famous efforts is the search for extraterrestrial intelligence, SETI, which seeks to detect signals from other advanced civilizations in the universe. Using powerful radio telescopes, SETI researchers scan the skies for signals that might be evidence of intelligent life. These efforts, while not yet successful in detecting alien signals, have expanded our understanding of the universe and pushed the boundaries of technology and scientific inquiry. But SETI is only one part of the larger search for extraterrestrial life. In recent years, astronomers have turned their attention to another area of great interest: the search for biosignatures, chemical signs that could indicate the presence of life on other planets. The search is based on the assumption that life elsewhere in the universe might share some basic characteristics with life on Earth, such as the presence of water and certain organic molecules. By studying the atmospheres of distant exoplanets, astronomers can look for these signs of life, such as oxygen, methane, and other gases that could be produced by biological processes. The discovery of exoplanets, planets that orbit stars outside our solar system, has revolutionized the search for life. In the past 2 decades, thousands of exoplanets have been discovered, many of which are located in the habitable zone, the region around a star where conditions might be suitable for liquid water to exist. The discovery of these exoplanets has opened up the possibility that there could be other Earth-like worlds out there where life might exist or could have existed in the past. The most exciting of these discoveries is the finding of Earth-like planets in the habitable zone of nearby stars. These planets, often referred to as Goldilocks planets, are considered to have the right conditions for life to thrive. They may have liquid water on their surfaces, a stable climate, and an atmosphere capable of supporting life. The discovery of such planets has led to the realization that there could be many more worlds out there that might harbor life, perhaps even life similar to our own. One of the most promising candidates for the search for life is Europa, one of Jupiter's moons. Europa has a subsurface ocean beneath its icy crust, and scientists believe that this ocean may contain the necessary ingredients for life. In 2020, NASA's Europa Clipper mission was approved to send a spacecraft to study the moon in detail, with the goal of determining whether Europa has the potential to support life. Europa's ocean is one of the most intriguing places to search for extraterrestrial life within our solar system. Another exciting possibility is Enceladus, a moon of Saturn. Like Europa, Enceladus has a subsurface ocean, and plumes of water vapor have been observed erupting from its surface. These plumes contain organic molecules, suggesting that the conditions beneath Enceladus's icy crust may be conducive to life. NASA's Cassini spacecraft discovered these plumes during its mission to Saturn, and future missions may focus on exploring Enceladus further to see if life exists within its ocean. Beyond our solar system, the search for biosignatures on exoplanets is expanding. Telescopes like the James Webb Space Telescope, scheduled for launch in 2021, will allow scientists to study the atmospheres of distant exoplanets in unprecedented detail. By analyzing the light that passes through a planet's atmosphere, astronomers can detect the presence of gases that are associated with life, such as oxygen, methane, and carbon dioxide. These gases, in the right combinations, could be evidence of biological activity. But what would it mean for humanity if we were to discover life elsewhere in the universe? The implications of such a discovery would be profound, touching on everything from science and philosophy to religion and culture. The discovery of extraterrestrial life would fundamentally change our understanding of life's origins and its place in the universe. It would challenge our assumptions about humanity's uniqueness and open up new questions about the nature of life itself. One of the most important questions that would arise from the discovery of extraterrestrial life is, what kind of life are we looking for? The search for life on other planets is typically focused on finding life similar to that on Earth. This is because we know that life on Earth relies on certain elements and conditions: water, carbon, nitrogen, oxygen, and others. However, some scientists speculate that life elsewhere could be radically different from life on Earth. It might not require water or carbon-based molecules. It might thrive in environments that are inhospitable to us, such as extreme temperatures, high radiation, or the absence of oxygen. The possibility of encountering such radically different forms of life raises even more profound questions. If we were to encounter alien life, how would we communicate with it? Would it even be possible to understand a life form with a completely different biology and way of thinking? The challenge of making contact with extraterrestrial life is not just one of science and technology, but also of philosophy and ethics. How should we approach the discovery of alien life? What responsibilities do we have to protect our planet and theirs? In addition to the search for life, there is also the question of intelligent extraterrestrial civilizations. Could there be advanced civilizations elsewhere in the universe, capable of sending signals or traveling across the stars? If so, why haven't we detected any signs of their existence? This question, known as the Fermi paradox, has puzzled scientists for decades. The universe is so vast with billions of stars and planets that could potentially harbor life. Yet we have found no definitive evidence of extraterrestrial intelligence. Some have speculated that intelligent civilizations might be rare, while others have suggested that advanced civilizations might be out of our reach, either because they are too far away or because they have self-destructed before reaching a point of interstellar communication. Despite the challenges, the search for extraterrestrial life remains one of the most exciting areas of scientific research. With each new discovery, from exoplanets in the habitable zone to the study of moons like Europa and Enceladus, we move closer to understanding the possibilities for life beyond Earth. Whether we discover microbes on a distant moon or make contact with an advanced civilization, the search for extraterrestrial life is a journey that will shape our future and redefine our place in the universe. As we look out into the vastness of the cosmos, we see a universe full of mysteries, challenges, and wonders waiting to be explored. While we've made remarkable strides in exploring our solar system, the question that looms larger than ever is, can humanity venture beyond the confines of our own solar system? The idea of interstellar travel has fascinated scientists, engineers, and dreamers alike for centuries, and as technology advances, the possibility of reaching other stars is slowly becoming less of a science fiction concept and more of a future reality. The concept of interstellar travel is as old as space exploration itself. The first human spaceflight, undertaken by Yuri Gagarin in 1961, showed the world that space travel was not just a dream, but something achievable. Since then, we have sent spacecraft to every major planet in our solar system, landed on comets, and even launched the Voyager probes, which are currently traveling beyond the influence of our sun. But these feats, impressive as they are only the beginning. The next great leap for humanity is not just beyond our solar system, but into the vast uncharted regions of interstellar space. At the heart of interstellar travel lies one fundamental challenge: distance. The nearest star system to Earth is the Alpha Centauri system, located about 4.37 light-years away. This might seem like a short distance in the grand scheme of the universe, but at current speeds, even our fastest spacecraft would take tens of thousands of years to reach it. For instance, the Parker Solar Probe, the fastest human-made object, travels at speeds of up to 700,000 kilometers per hour, about 430,000 miles per hour. At that speed, it would take over 17,000 years to travel just 1 light year. Clearly, we need far faster spacecraft to make interstellar travel feasible within a human lifetime. To overcome these vast distances, new forms of propulsion and energy will be required. Conventional rocket technology, like the engines that have propelled us to the Moon and Mars, simply won't cut it for interstellar missions. Instead, we need to explore revolutionary concepts in propulsion technology, many of which are still in the early stages of development. One promising avenue is the idea of using nuclear propulsion. The concept of nuclear-powered spacecraft has been around for decades, And the idea is relatively simple. Use nuclear reactions to generate much higher levels of energy than conventional chemical propulsion systems. In theory, nuclear-powered engines could allow spacecraft to travel much faster, possibly reaching a significant fraction of the speed of light. This type of propulsion could dramatically reduce travel time to other star systems. There are several approaches to nuclear propulsion, each with its own advantages and challenges. One possibility is nuclear thermal propulsion, which involves heating a propellant like hydrogen using a nuclear reactor and expelling it through a nozzle to generate thrust. This system could theoretically be much more efficient than conventional chemical rockets, allowing spacecraft to reach higher speeds with a smaller amount of fuel. Another approach is nuclear electric propulsion, where nuclear reactions are used to generate electricity that powers ion thrusters, engines that use electric fields to accelerate charged particles to very high speeds. While ion thrusters provide much lower thrust, they are incredibly efficient and could allow a spacecraft to travel continuously over long distances. The most ambitious proposal for interstellar propulsion, however, is the breakthrough Starshot project. Announced in 2016, this initiative aims to send small, lightweight probes to Alpha Centauri within a generation. The idea is to use a powerful laser array to accelerate tiny, flat star chips to speeds of up to 20% of the speed of light. At this speed, the probes could reach Alpha Centauri in just over 20 years, a time frame that is within the realm of possibility for human lifetimes. These probes would carry no human passengers, but they could transmit valuable data back to Earth, giving us our first close-up look at another star system. While this technology is still in its infancy, the Starshot initiative is a bold step toward interstellar travel. It showcases the potential for harnessing cutting-edge technology to send probes, and eventually, perhaps even humans, across the vast expanse of interstellar space. But sending probes to other star systems is just the beginning. For humanity to truly become a spacefaring species, we must also tackle the challenges of living and surviving in deep space for extended periods. Living on spacecraft for decades or even centuries presents a host of challenges. First and foremost, astronauts will need a reliable source of food, water, and oxygen. For missions to far-off star systems, carrying enough supplies for the entire crew would be impractical. Instead, future spacecraft may need to rely on closed-loop life support systems, systems that recycle air, water, and waste products, making it possible to sustain human life for extended periods without resupply from Earth. In addition to food and water, future spacefarers will need protection from the dangers of space radiation. In low Earth orbit, the planet's magnetic field provides a natural shield from harmful cosmic radiation and solar particles. However, once humans venture beyond the protective atmosphere of Earth, they will be exposed to high levels of radiation that can damage cells, tissues, and DNA. To mitigate this risk, future spacecraft may need to incorporate advanced shielding, such as hydrogen-rich materials or magnetic fields that mimic Earth's natural defense systems. Another critical consideration for long-duration interstellar missions is psychological well-being. Spending years or even decades in the confined, isolated environment of a spacecraft could take a serious toll on the mental health of astronauts. The lack of social interaction, the monotony of daily life, and the constant exposure to the challenges of space travel could lead to stress, anxiety, and depression. Scientists will need to develop strategies to address these psychological challenges, such as creating virtual reality environments, maintaining regular communication with Earth, and fostering a sense of community among the crew. Once we overcome the technological and psychological hurdles of interstellar travel, there is the potential to explore alien worlds. As we've already seen, there are countless exoplanets in the universe, many of which are located in the habitable zone of their parent stars. Some of these planets may even have the conditions necessary for life to thrive. If humanity reaches these distant worlds, we may find signs of life, or perhaps even intelligent beings. This discovery would be one of the most profound moments in the history of human civilization, redefining our understanding of life, our place in the universe, and our future. But even if we don't find extraterrestrial life, the journey itself would be of immense value. The exploration of alien worlds would provide us with a deeper understanding of the processes that shape planetary systems, the origins of life, and the potential for humanity's future in space. It would expand the boundaries of human knowledge and offer new opportunities for growth and discovery. The possibilities are endless, and the future of space exploration is full of promise. As we look toward humanity's future in the stars, we are reminded of the immense challenges and the incredible opportunities that lie ahead. The road to interstellar travel may be long and fraught with difficulties, but it is a journey worth taking. Whether we send probes to distant stars or one day set foot on an alien world, the dream of becoming a spacefaring species will shape the future of humanity and ensure that our exploration of the universe is only just beginning. As we venture further into the cosmos, it becomes clear that space exploration is not just about discovering new worlds or reaching distant stars. It's about understanding our place in the universe, pushing the limits of human knowledge, and ensuring the long-term survival of humanity. The journey into space has already transformed our world in profound ways, and the future promises even more groundbreaking discoveries. But beyond the scientific and technological advances, space exploration has a unique ability to inspire, foster cooperation, and challenge us to think beyond our immediate horizons. One of the most significant impacts of space exploration has been its ability to drive technological innovation. The challenges of exploring space, whether it's designing spacecraft that can survive the harsh conditions of space, developing life support systems for long-duration missions, or finding new ways to communicate across vast distances, have pushed the boundaries of engineering and technology in ways that have benefited life here on Earth. Many of the technologies that were initially developed for space missions have found applications in everyday life. Take, for example, satellite technology. Satellites are used for a wide range of purposes, including communications, weather forecasting, navigation, and global positioning systems, GPS. These satellites have revolutionized the way we live, making it possible to connect with people across the globe, predict natural disasters, and navigate with incredible precision. Another example of space-driven technology is medical advancements. The need for medical systems capable of supporting astronauts during extended space missions has led to breakthroughs in fields such as telemedicine, medical imaging, and remote diagnosis. In addition, the development of life support systems for space missions has led to improvements in water purification and air filtration technologies, which are now used in hospitals, disaster relief efforts, and areas with limited access to clean water. Materials science is another area that has benefited from space exploration. The extreme conditions of space, vacuum, radiation, and temperature extremes have prompted the development of new materials that are stronger, lighter, and more durable. These materials are not only used in spacecraft and satellites, but have also found their way into a variety of industries, from aerospace to construction to electronics. The advancements in technology driven by space exploration have created ripple effects throughout society, leading to innovations in industries ranging from agriculture to energy to telecommunications. By pushing the boundaries of what is possible, space exploration has made a lasting impact on our daily lives, and it will continue to drive innovation for generations to come. But the benefits of space exploration are not just technological, they are also deeply humanitarian. Space exploration fosters international cooperation in ways that few other endeavors can. The challenges of space exploration are so immense, and the rewards so significant, that countries across the globe have come together to work toward common goals. The International Space Station, ISS, is one of the most remarkable examples of this collaboration. It's a joint project involving the United States, Russia, Japan, Canada, and the European Space Agency, and it has been continuously inhabited by astronauts from different countries for more than 2 decades. The ISS serves as a testament to the power of cooperation and the shared goals of exploring space. Astronauts from various countries live and work together in this orbiting laboratory, conducting experiments that help us understand everything from human health to the behavior of materials in microgravity. The ISS has become a symbol of peaceful collaboration in space, showing that when nations put aside differences and work together, incredible things can be accomplished. Moreover, the pursuit of space exploration has encouraged the development of global partnerships. The challenges of sending humans to the moon, Mars, or beyond will require collaboration across nations, industries, and academic institutions. This collaboration isn't just about sharing resources and technology. It's also about sharing knowledge, expertise, and a common vision for humanity's future. The United Nations has recognized the importance of space as a shared resource, and there have been international agreements in place to ensure that space exploration is conducted in ways that benefit all of humanity. The Outer Space Treaty, signed by over 100 countries, states that space exploration should be conducted for the benefit of all nations, and that space should be free for exploration and use by all. As countries and organizations continue to collaborate in space, the potential for peaceful cooperation and shared discovery is limitless. Space exploration has the power to unite people around a common cause, one that transcends national borders and challenges the limits of human knowledge. The idea of working together to explore the cosmos can be a powerful force for global peace and understanding, encouraging collaboration over conflict. However, beyond the cooperation, space exploration also serves as a powerful source of inspiration. The achievements of space exploration, such as the Apollo moon landings, the Mars rovers, and the Voyager probes, inspired generations of scientists, engineers, and dreamers to think big and pursue their passions. The images of Earth from space, the breathtaking photos of distant galaxies, and the stories of astronauts exploring strange new worlds captivate our imaginations and encourage us to ask big questions about our place in the universe. One of the greatest gifts of space exploration is the way it ignites curiosity. For children and young adults, the idea that there are unknown worlds and distant stars waiting to be discovered can spark a lifelong interest in science, technology, engineering, and mathematics, STEM. The next generation of space explorers, scientists, and engineers is already being inspired by the achievements of those who came before them, and they will go on to push the boundaries even further. Space exploration also encourages critical thinking and problem-solving skills. The challenges of operating in space, dealing with limited resources, ensuring the safety of astronauts, and solving problems in real time require creative solutions and innovative thinking. These skills are transferable to a wide range of fields and are invaluable in solving some of the world's most pressing problems, from climate change to energy sustainability. In addition to inspiring future generations, space exploration offers a unique perspective on our own planet. When astronauts look down on Earth from space, they are struck by the fragility and interconnectedness of our world. The overview effect, as it's called, is a profound shift in perception that astronauts often experience when they see Earth from orbit. From space, the boundaries that divide nations and cultures disappear, and the Earth becomes a single, fragile entity floating in the vastness of space. This perspective has inspired many astronauts to become advocates for environmental protection and global cooperation, seeing the Earth as a shared home that must be protected for future generations. But perhaps the most profound aspect of space exploration is the way it challenges us to think beyond our earthly concerns. It forces us to ask the most fundamental questions. What is our place in the universe? How did life begin? Are we alone in the cosmos? These questions touch on everything from science and philosophy to religion and the future of humanity. Space exploration encourages us to look beyond the confines of our planet and consider the possibilities of life elsewhere in the universe, the origins of our own existence, and the fate of humanity in the vast expanse of time. As we continue to explore the stars and beyond, space exploration will continue to shape the future of humanity. It will push the boundaries of science and technology, inspire new generations of explorers, foster global cooperation, and provide a new perspective on our place in the universe. The journey is only just beginning, and the possibilities for discovery, growth, and understanding are endless. As humanity ventures deeper into the cosmos, exploring distant planets, moons, and stars, we are faced with profound ethical questions about how we should interact with space and its resources. Space exploration offers vast opportunities for discovery and advancement, but it also brings with it a set of ethical dilemmas that must be carefully considered. As we look toward the future of space exploration, we must ask ourselves, how should we explore space responsibly? What rights do we have to the resources of other planets? How do we preserve the integrity of space itself? At the heart of these ethical concerns is the question of planetary protection. How do we prevent contamination of other planets and moons with Earth-based life forms and vice versa. The issue of planetary protection is critical to ensuring that we do not inadvertently introduce harmful microorganisms from Earth into alien environments, which could disrupt their ecosystems or lead to irreversible changes in their natural states. Similarly, we must also consider the possibility of contaminating our own planet with alien microbes should we discover life elsewhere in the universe. One of the primary goals of planetary protection is to ensure that any life we discover on other planets is not compromised by our presence. In 1967, the Outer Space Treaty was established, which includes provisions for preventing harmful contamination of space and celestial bodies. The treaty emphasizes that space exploration should be conducted for the benefit of all nations, and that activities in space should be undertaken with respect for the environment and the possibility of extraterrestrial life. However, while the Outer Space Treaty provides a framework for space exploration, the issue of planetary protection remains an ongoing concern, especially as space missions become more ambitious and the prospect of human colonization of other planets becomes increasingly likely. As we send probes to distant planets such as Mars and consider the possibility of sending humans to the Moon or even Mars in the future, we must ensure that we adhere to strict sterilization protocols to prevent contamination. For example, spacecraft that land on Mars are thoroughly cleaned and sterilized to ensure that no terrestrial microorganisms hitch a ride and potentially alter the Martian environment. These precautions are vital for preserving the integrity of alien ecosystems and ensuring that we don't interfere with any possible native life forms. Another key ethical concern is the mining of extraterrestrial resources. As we explore new planets, asteroids, and moons, the potential to mine resources such as water, metals, and rare minerals becomes increasingly real. For example, asteroids are believed to contain vast quantities of valuable metals such as platinum, gold, and nickel, which could be used to support human activities both on Earth and in space. Some even argue that the mining of these resources could help alleviate resource scarcity on Earth and serve as a stepping stone for future space colonization. However, the prospect of mining other planets raises significant ethical questions. Should we have the right to extract resources from other celestial bodies? Many experts argue that the resources of space should be treated as common heritage, not to be exploited for personal gain. The Moon Agreement of 1979, which was signed by a limited number of countries, stated that the Moon and other celestial bodies are not subject to national appropriation or ownership, and that their resources should be used for the benefit of all countries. This raises the question of whether the commercialization of space and the exploitation of resources should be regulated by international law to prevent monopolies or conflicts over access to these resources. The ethical issues surrounding the mining of extraterrestrial resources are compounded by the potential for environmental degradation. While space is vast and seemingly infinite, it is still a fragile environment. The extraction of resources from other planets or moons could lead to the destruction of alien landscapes, the depletion of essential materials, and the creation of space debris. The development of sustainable space exploration practices, including the responsible use of extraterrestrial resources, will be essential to ensuring that we do not damage the very environments we are trying to explore. In addition to the environmental and resource-related concerns, space exploration also raises questions about the rights of future space colonists. As we consider the possibility of establishing permanent human settlements on the Moon, Mars, or beyond, we must think about the ethical implications of colonizing other worlds. Who will have the right to live and work in these new frontiers? Will space colonies be governed by the same laws and principles that we follow on Earth? Or will new legal and ethical frameworks need to be established? One of the key ethical issues surrounding space colonization is the question of ownership. If humanity establishes colonies on other planets, who owns the land? If a private company is responsible for funding and building a colony, will it have the right to claim ownership of that land and its resources? This question is further complicated by the fact that the Outer Space Treaty states that no nation has sovereignty over any part of space or celestial bodies. In theory, this means that no government, corporation, or individual can claim ownership of land on other planets. But as the technology for space colonization becomes more feasible, we may need to revisit this legal framework and determine how ownership and governance will work in these new, uncharted territories. There is also the issue of intergenerational ethics. If we send humans to settle on other planets, it will likely be a multi-generational endeavor, with generations of people living and working on these colonies for hundreds or even thousands of years. How do we ensure that these future generations have the right to thrive and prosper? What responsibilities do we, the current generation, have to ensure that they inherit a world that is capable of sustaining life and providing for their needs? Intergenerational ethics will be critical in shaping the long-term future of space colonization and the ethical obligations we have to future explorers and settlers. As we continue to push the boundaries of space exploration, we must also consider the social and cultural implications of venturing beyond our planet. Space exploration has historically been seen as a unifying force, something that brings nations and cultures together in the pursuit of common goals. The Apollo moon landings in the 1960s and 1970s were a source of global pride, and space exploration continues to inspire people of all ages and backgrounds. However, as space travel becomes more accessible and commercialized, it raises questions about who will have access to space and who will be left behind. As commercial space travel becomes more affordable and widespread, it is likely that space will become a destination not just for governments and astronauts, but for ordinary people as well. Space tourism is already becoming a reality, with private companies like SpaceX, Blue Origin, and Virgin Galactic working to offer suborbital flights for paying customers. While this is an exciting development, it also raises concerns about equity. Will space exploration remain the domain of the wealthy, or will the benefits of space travel be shared by all people, regardless of socio-economic status? Another important question is the impact of space exploration on Earth's environment. As space exploration becomes more commercialized, the launch of rockets and the growth of space infrastructure will likely increase the amount of space debris. Space debris, spent rocket stages, defunct satellites, and other pieces of discarded equipment already poses a significant risk to satellites and spacecraft. How can we ensure that the pursuit of space exploration doesn't exacerbate the environmental challenges we face here on Earth? creating sustainable, environmentally responsible space missions will be essential to preserving the long-term viability of space exploration. As we continue to explore the stars, it is essential that we approach space exploration with an awareness of the ethical responsibilities we carry. From planetary protection to the governance of space colonies, the future of humanity's relationship with space will require thoughtful consideration, collaboration, and a commitment to doing what is best for all of humanity, both now and in the future. Thank you so much for joining me on this incredible journey through the cosmos. From the birth and death of stars to the search for extraterrestrial life, we've only scratched the surface of the vast universe that surrounds us. If you enjoyed this deep dive into the mysteries of space, don't forget to hit that like button and subscribe to the Sleepy Science Facts for more peaceful explorations and soothing content. Your support helps this channel grow and brings more cosmic wonders to curious minds like yours. Let me know in the comments what part of the universe you'd like to explore next. Until then, keep looking up and stay curious. Sweet dreams, and I'll see you in the next video.